So in the last part of this lecture, we emphasized that the correct quantity, the thermodynamic quantity to look at under constant pressure and temperature is the Gibbs free energy, or the change in Gibbs free energy, because if that change in Gibbs free energy is negative, then the process is spontaneous, and if we are considering some equilibrium process, so that will be 0, and this is the Gibbs free energy change of the system. So now we are going to actually consider how this Gibbs free energy changes with respect to parameters like pressure and temperature, and how we can actually use it for discussing chemical or physicochemical transformations. Now, one of the very interesting things, if you remember that equation for dg, we did not write it in the last part. So dg will be s dt minus VdP, and minus SdT plus VdP, and then we can actually very easily see that this del G del T P, so that will be, if I keep the pressure constant, so this term goes to 0, and that will be nothing but minus S, and similarly del G del P T is V. Now, what are the implications of this equation? So let us draw a diagram just to give you a feeling how the Gibbs free energy changes with respect to temperature and pressure. So if I increase the temperature and if I plot how the Gibbs free energy changes, now that is equivalent to the change in entropy, but with a negative sign. Now, the absolute entropy, according to the third law of thermodynamics, which we have not discussed so far, so there could be a residual entropy in the system, but entropy is always positive, it's 0 or positive. Now, in a very ideal close to 0 temperature, the entropy is 0, but always you will have a residual entropy. So we can say that entropy is always positive, in the sense that the slope of this curve del G, G versus T at constant pressure will be negative. Now, if we take a gaseous substance or a vapor substance in a vapor phase, the slope, usually the molar entropy of or the entropy of the gas will be very, very high. So we'll start from a very high point compared to liquid and solids, and the decrease will also be much steeper. Compared to liquids, we'll start somewhere at a below the gaseous entropy value. So it will be it will have some slope, but of course it will be less, and for solids it will be even less. It will be something like this. Now it's not increasing, so let me just redraw the liquid and solid curves once again. So let's say the liquid is something like this and the solid is something like this. So everybody is decreasing, but the liquid and the vapor, solid and the vapor, the decrease is at a much lower rate than the solid. So if we plot it, the variation of the Gibbs free energy with respect to temperature at constant pressure, so we'll get a curve, and the slope of this curve will be equal to the change in entropy, and or the absolute entropy. Now, as you see here, so the slope is given by the del G del T P, and that is minus S. Now, S is always positive, and then minus S will be always negative, but for gaseous substance the slope will be much higher, and also see that we are starting from a very high value. For liquids, it will be slope will be less, because the entropy of liquid is less than the gas, so it will be something like this, and for solids it will be even less, and then the change will also be at a much smaller rate. So we'll have a typical curve like this, where this is for the vapor phase, this is for the liquid phase, and this is for the gas phase. And similarly, if we want to study the variation of the Gibbs free energy versus pressure at constant temperature, so the slope is equal to the volume. Now, of course, for it is a volume is a positive quantity, it will increase, but for solids, for example, there will not be much change, so it will be almost flat to the x-axis, something like this. For liquids, it will slightly increase, not decrease, So we can actually say it will be slightly increasing. For liquid, it will be a little bit increasing, a little bit more than solid, but again liquids are less compressible, so the volume will not change much. For gas, it will keep on increasing. Now the question is how it will increase. Will it increase linearly? But we know that if the from ideal gas equation, that if I increase the pressure, the volume will actually drop. So this is actually a positive number, but the slope, as we can see, will change as we are increasing the pressure. So the curve will look like something like this, because as you can see here, the slope here and the slope here are actually different. The slope here is much more than the slope here. So the gas will have a curved plot for G versus T, G versus P. Now the question is, if we actually vary the pressure and temperature simultaneously, the question is how will you generate surface or generate a Gibbs free energy change, how will you plot that thing. Now the interesting thing is that this condition that we have already written, that del G has to be equal to 0 if there is an equilibrium. Now you can see from this curve that the solid and the liquid are basically crossing at some temperature, and similarly the liquid and the gas are also crossing at some temperature, which means at this temperature, at that particular pressure, for this curve actually kept the pressure constant. For that pressure at this temperature, this defines actually a condition where the Gibbs free energy, because the y-axis was Gibbs free energy, for the gas as well as the liquid at the same, which means actually the liquid and the gas are in equilibrium. And in this case, actually this is this point which I'm drawing right now is basically an intersection of the liquid and the solid line. So this should be S, and then if the liquid and the solid are in equilibrium, that temperature we call as the melting point or the freezing point. And similarly, at this temperature, as you can see here, the vapor and the liquid lines cross, and then we call it as a boiling temperature. So we write it as a TB. So we'll come back to it. I will draw it more clearly and see what are the effects of that. And of course, we see that there is a cross point for solid and liquid also, but that point is lying much higher. So as you can see, that what are the implications of these lines is that say for example, if I take a arbitrary temperature at a fixed pressure, this is all drawn for a fixed pressure. So at this temperature, we see the solid curve is lying much lower. So which means the Gibbs free energy of the solid is much less compared to the Gibbs free energy of liquid or gas or vapor. So we see that the solid is the most stable phase at this temperature and pressure. Similarly, if I draw a line here, I see that the vapor is the most stable phase here. So similarly, this solid to liquid transition will not happen at this pressure the way we have drawn it, because I see that up to the TF temperature, this entire region, the solid is the let me actually use some other color. So the solid is the most stable form. So this region, because this curve for the solid actually lies lower, and then there is a region where actually the liquid is the more stable region. So this region, as you can see, and then above that the gas is the most stable region. So we see this particular region, the vapor has the least Gibbs free energy. So we see actually a transition from solid to liquid and liquid to vapor in this diagram, and how we can increase the temperature keeping the pressure constant. Now the question is, if we actually vary the pressure and temperature simultaneously, how it will look like. And definitely, so there will be some, we can actually draw some lines where the Gibbs free energy change is 0, or meaning the two phases are in equilibrium. And that particular diagram, which we call as a phase diagram, which is actually a variation of the pressure versus temperature, and we are drawing some lines, and those lines represent basically the conditions for equilibrium between two phases, is known as a phase diagram. So I'll draw a typical phase diagram, and it looks like something like this, and we are plotting it, say pressure versus temperature. So what we see here, that here this region we call it as a vapor region. So at a say very high temperature and low pressure region. So this will be the region of the vapor, and this will be the region of the solid, which is at a very high pressure or low temperature, and similarly this will be the region for the liquid. And these lines represent the line or the which represent the basically phase transitions, and on these lines the Gibbs free energy of the two phases are equal. So basically if I want to write down an equation for this line, so it will be something like Gibbs free energy per unit mole, which we also call as chemical potential. We have not discussed about chemical potential until now. So chemical potential is defined nothing but the Gibbs free energy per unit mole. So this chemical potential or the Gibbs free energies per unit mole must be equal for the solid and the liquid, solid and the vapor, because it's the line which is joining the solid and the vapor. And similarly this line will represent a region where the liquid is in equilibrium with the vapor, and similarly for this line the solid is in equilibrium with the liquid. So we see that under a particular combination of pressure and temperature, one phase will basically dominate. Suppose if I choose a particular point in the phase diagram, suppose this point. So this point represents a particular combination of pressure and temperature, and that pressure temperature we see the Gibbs free energy is minimum for the vapor phase. So the substance will actually exist as a vapor. So what we do is that for various substance we actually draw a phase diagram, because phase diagram is very fundamental to our understanding, and it will give you every information how one phase actually gets transformed to the other phase and under what conditions or a particular phase is stable. Now we see that these three lines are actually meeting at a point, which means at this point all these three phases are in equilibrium, meaning we have a very interesting condition here that the chemical potential of the solid is identical to the chemical potential of the liquid, which is also identical to the chemical potential of the vapor. So this pressure temperature combination where actually the three phases coexist, we call it as a triple point. Similarly, the point up to which the liquid vapor phase exists. Now whenever we talk about phase, we talk about basically an existence of a phase boundary between two macroscopic phases. Just something like you have a glass of water, say, and say for example I have a water, and we can see the water has a surface. So and then we say that this is basically a phase boundary. This is a liquid water, and then the water is in equilibrium with water vapor. Because this is a closed system, so some water will vaporize, but then quickly it will reach the vapor pressure. So then no further evaporation, net evaporation will happen. I mean, molecules are of course leaving the surface, and the molecules which are also coming back to the liquid from the vapor phase. So this will be under equilibrium, and then we'll have a vapor in equilibrium with its liquid, which is right now the situation. And the two phases, the vapor phase and the liquid phase, are separated by a well-defined boundary that I can see here. But if we actually keep on heating any substance, something like say water, liquid water, then we'll actually see at a particular combination of temperature and pressure, the phase boundary vanishes. And this thing we usually discuss when we talk about the properties of real gases, where we show that okay, so after a certain point you do not see any you do not see any particular appearance of the boundary. So the boundary all of a sudden vanishes, and that point you call as a critical point. So above the critical point, you have actually a state which is known as a supercritical state. It behaves as a vapor like, but it is not a true vapor. It is neither vapor nor liquid, so it's called as a supercritical liquid. Now the phase diagram, as I have drawn here, represents a typical phase diagram again, but of course the slope of this solid liquid curve needs some attention, because the way I have drawn it, solid liquid curve slope is something like this. It is very much exaggerated because it will be the slope will be much less compared to the solid vapor or the liquid vapor slope, and it will be something like a steep slope, but the question is whether it is a positive or negative slope. Now it will be a positive slope. Now what is this slope? Let us try to first understand. Now this slope means actually it's a slope of this curve, which is dp dt. So that slope. Now you can show that again from the very fundamental equation that we have the alpha phase or basically the chemical potential of a particular phase and chemical potential of the other phase, and you can show that this ultimately, if I want to write an equation, that will be basically dictated by how much change you have in the chemical in the molar volume. So as you can see here, so if I want to actually we'll come to that full equation, but before that, let's say if I just change the pressure with respect to or change the temperature keeping the pressure constant, that we already discussed. But here if you see, if I change the pressure with keeping the temperature same, that is nothing but equal to volume. So if I were talking about say the change in chemical potential with respect to pressure keeping the temperature constant, so chemical potential is nothing but the Gibbs free energy per unit mole. So we can write this like this, and so ultimately we will have nothing but V divided by N, and V divided by N is nothing but molar volume, which we write as V bar, or we write it as V suffix M. So what we see here is that if I apply pressure keeping the temperature more or less constant, which is somewhere here, so like I'm assuming this change in temperature is small, so then we can say that it will depend on the difference in the molar volume. Now for a substance like say carbon dioxide, going from say solid to liquid, because we are traversing, if I go from here to here, so it is basically we are going from solid to liquid region, and if I go from solid to liquid, you will see that the liquid volume is large than the solids volume. So basically the slope more or less equal to the change in the molar volume solid to liquid transition, which is basically molar volume of the liquid minus molar volume of the solid, or let us actually use the V bar notation and subscript as liquid minus solid, and that will be basically the slope will be proportional to that. And then what we argue is that that is positive for a substance, let's say for carbon dioxide. But for water, we know when ice melts into water up to 4 degrees centigrade, 0 degree to 4 degrees centigrade, the ice structure actually collapses, because ice has a very much open structure which you have studied. It has a like one water molecule is tetrahedrally surrounded by 4 water molecules like this, which you have already studied, and this is through hydrogen bonding, you know about this. And that hydrogen bonding is basically causing the ice to have a more open like structure. So we can just clearly show this thing. So these are the covalent bonds, and plus every water molecule will also have hydrogen bond. So this is kind of the structure of ice which we kind of accept. It's not a fully correct structure, but it has an open structure like this, and then when it melts, the volume actually collapses. So for that, the slope is negative for water. So this particular slope, the way we have drawn it, will be something like this, and the slope will be negative. So the way we should draw the phase diagram for ice or a phase diagram for water is something like this. But again, this is an exaggerated drawing. It won't be exactly like this. It will be, the slope will be very less, because the change in the molar volume again will be much smaller per change in the per degree rise in the temperature. Now, so the phase diagram will basically will tell you how, what temperature and pressure combination one particular phase is most stable, and secondly, where the phase boundaries exist, how and at what temperature and pressure you can actually switch from one phase to the other phase. Now, when we talk about these phase diagrams, so we actually talk about this slope of this curve dp dt, and that is the most important for phase transitions. Now the question is, if we consider say solid liquid equilibrium, so for solid liquid equilibrium, now you can think what will be the dp dt. Now dp dt, now you can show that from, again, starting from the very fundamental equation which we had written for dg. Let us go back. So we know that dg is minus s dt plus v dp. So what we have to do here is we are talking about the dg per unit mole. So we can write it as d mu is minus s dt plus v dp, but this is for particular phase, let's say phase alpha. So I can write it as S alpha and V alpha, and since I am writing mu, I have to use V bar and S bar notation because it's a molar entropy and molar volume. And similarly, we can write it for another phase which is beta, like d mu beta is something like minus S beta dt plus V beta dp. And at the equilibrium, we know that d mu alpha is nothing but equal to d mu beta, and from that you can actually equate all these two equations, and you just collect the dp terms and the dt terms, and then what you will see here, this will be nothing but dp dt is nothing but the change in the molar entropy or S bar, and divided by the change in the molar volume. Now this is the change during a phase transition, because only for the phase transition we have this condition that d mu alpha equal to d mu beta, because the two phases are in equilibrium, which means the Gibbs free energies are equal or the chemical potentials are equal. So we actually write it as a transition. So delta suffix transition means actually for a particular transition. For example, if we are talking about solid liquid equilibrium, for solid liquid equilibrium, this equation, which is dp dt, is so this equation is known as Clapeyron equation. So there is a S bar, don't forget, it's a molar quantity. So this is known as Clapeyron equation, and the Clapeyron equation takes different form if we talk about different equilibrium. For solid liquid equilibrium, this dp dt will be nothing but, so delta S fusion. So if we during the phase transition, so the associated heat change or the reversible heat change is nothing but equal to the enthalpy, because we know that when the phase transition is happening, it is happening at constant pressure and temperature. So delta S we can actually replace by delta Q reversible by T, which is actually delta H by T, and that process we call it as a fusion. It's a solid to liquid equilibrium and vice versa. So we write the transformation as fusion. So that's why I'm writing a FUS subscript. It will be delta H divided by it is a dq reversible by T, if you remember the change formula for entropy, and we'll have T delta fusion into molar volume, and this is also molar enthalpy. And then we can actually integrate this equation, and after a few approximations you can show that the pressure will be approximately equal to some initial pressure, which I am calling as P star, plus delta fusion H divided by T star. So T star is the temperature corresponding to pressure P star, and delta fusion V into T minus T star. So that is how the pressure actually goes with the integrated form, how the pressure actually varies with temperature. So if I know that thing, that basically tells me the equation of that line. Which line? Which is the solid liquid phase boundary. So the equation of this line is something like this, and as we can see, it's a linear equation. So it depends, of course, on the change in the molar volume, so this quantity. So and as we can see that it is nothing but P minus P star is something like, if we can write it in a simpler way, so P minus P star is basically proportional to T minus T star. But it depends on the proportionality constant. If this constant is positive, so then I'll have a linear increase, and if this is negative, like for water, you will have a negative slope. So that's what we are trying to tell when we are discussing the slope of this solid liquid equilibrium phase boundary. Now similarly, we can actually think about liquid vapor equilibrium or the solid vapor equilibrium. The solid vapor will not discuss because it will be just like the liquid vapor equilibrium. For liquid vapor equilibrium, this slope dp dt, now which is actually which has a thing like we can always write it as a the transformation as a vaporization in this case. So and again we can actually say that the change in entropy at constant pressure is nothing but dq reversible by T, and at constant pressure dq is nothing but dH. So we can write it for of course for a reversible process, and we are considering an equilibrium and we are assuming reversibility. So divided by T into delta vaporization into molar volume. So that eventually you can actually now use PV equal to the ideal gas equation for one phase, which is the vapor phase. And if you use that, then you can actually get a simpler form for this equation, and that is now as you can see, this T actually you can write it as a RT by P, and then you can do all the manipulation, not the T, sorry, the delta vaporization of V. So there will be two volumes, and one of the volumes you can actually write it as RT by P, and then finally it will be dP by P, and which you can actually write dln P dt is delta vaporization H divided by RT square. Now this equation either in its differential form or in the integrated form is known as, remember that the original equation was known as Clapeyron equation for the general equation of phase transition, and then we approximated it for solid liquid equilibrium, so for solid vapor equilibrium. So this modified form of the Clapeyron equation is known as Clausius-Clapeyron equation. Now you can further integrate the Clausius-Clapeyron equation and then get a relationship how the pressure varies with temperature in an integrated form, and then that you will see that it will be something like e to the power minus delta vaporization of H. So I should write it as a delta vaporization of H. So it's a enthalpy change for vaporization divided by R into 1 minus T minus 1 minus T star, where actually the pressure, if the pressure is P, the temperature is T, and the initial pressure we took as P star and the initial temperature was T star. So this is the integrated form of this Clausius-Clapeyron equation. And thus we see that starting from our very basic fundamental understanding that how one should look at the spontaneity and or the equilibrium of the process from the system's perspective, we said that most of the chemical transformations are undergoing under constant temperature and pressure. So the Gibbs free energy is the correct quantity to look at, and if we actually see or analyze the Gibbs free energy, then we find that this change in the Gibbs free energy can happen with respect to pressure and temperature, because these are the natural choices. And if we vary those conditions, how the Gibbs free energy is changing, and then we figured out that it will be very important for phase transition, where actually one phase is basically transforming into the other phase, and there is a equilibrium between the two phases at a particular pressure temperature. So that equilibrium denotes actually the existence of a phase boundary, and we basically derive the equations for those lines which actually separates the two phases in a phase diagram. And that is basically the Clausius-Clapeyron equation. And then the next thing what we do is that, depending on the nature of this phase transition, we also talk a little bit about the classification of this phase transition, and which is known as RN phase classification. We talk about first order phase transitions, we talk about second order phase transitions, we also talk about some other phase transitions which you cannot categorize as first order or second order phase transitions. Now, before I conclude this part, let us actually have a discuss about the what will be the effect of say, if I apply pressure, how what will be the effect on the freezing point and melting point. So we are actually trying to go back to this curve which we draw very early here. So we want to actually want to study or see if I actually apply pressure, how basically the melting point and the freezing points are going to change. So let us just draw this figure once again more clearly. And so what I'm saying here, I have a G versus or mu versus T curve for the solid, which I wrote as the black curve, and then let us draw another curve, let's say in blue, for the liquid. Suppose this is something like this, and then we also have a curve for the solid, and let us actually draw a curve like this. So the solid and liquid, the difference will be less. So that's why the drawing has to be very perfect, and then we have something like this. All right. So now see, the freezing point is basically the intersection of the curves which are the intersection of the solid and the liquid. So we just write it as TF, and similarly the melting point the boiling point is basically the intersection of the liquid, which is the blue curve, and the black curve, which is the vapor curve. So that is the boiling point. Now suppose I am applying pressure, and I want to understand how these curves are changing. Particularly the freezing point. We'll just talk about the freezing point thing for the time being. So let me actually draw it once again. So freezing point is nothing but the intersection of the solid and the liquid. Now suppose I am actually exaggerating that curve. So for liquid I was using blue line, and suppose that the In the normal case, as you know that, let's just draw it once again. Suppose I'm zooming this these two curves. These two curves means just the blue and the red curve, and if I zoom that, so suppose this is the original blue curve which is at a low pressure, and then there is a red curve which is also at a low pressure. And now we'll see the effect of increase of the pressure on this, and this is basically, we call that as a normal freezing point, or TF. So this is again T versus mu curve, or T versus G curve. If it is per mole, then it is mu. Now so this is the normal freezing point at that temperature. The Gibbs free energy for the red curve and the blue curve are the same, which means the two phases are in equilibrium, which happens during freezing, basically melting. Now if I apply the pressure, if the change in the molar volume, because you know that if keeping the temperature same, if I apply pressure, so what will happen? So the equation is del G del P, keeping the temperature same, is nothing but equal to the volume. Now if I use Gibbs free energy per unit mole, which is nothing but mu, this will be molar volume, but it's not necessary to use the molar volume concept. It's just suppose the volume for some fixed amount of mole. And if we just think about that, the change in the molar volume at a very high pressure, the molar volume, what it is going to happen. So basically at low pressure, the molar volume for a let's think for a liquid, there will be some change in the molar volume. Usually at a higher pressure, the change in the molar volume will be basically much less, and in the solid also the change in the molar volume will be much more less. So in the sense that if I actually apply pressure, of course the molar volume is going to decrease because I'm actually applying the pressure. And now the question is, if this is at a low pressure curve, where the high pressure curve will lie. So for liquid also, what I'm saying, it will drop, say it is dropping like this, but it will be a kind of parallel line with respect to the original line. Why it is parallel line? Because if you remember that suppose we are keeping temperature constant, suppose some temperature. At this temperature, I am asking if I apply pressure, what will happen? So just the volume, since it is proportional to the volume del G del P at constant temperature, the molar volume is decreasing. So I'll just have a decrease in the in this curve, and then basically I'll have an increase in the curve.